Thank you all for coming to Journal Club, especially you, Hanyan.
As always.
Today we'll be talking about the Nonabelian quantum Fourier transform as kind of a part two to my talk last week on the abelian quantum Fourier transform. And so, as I mentioned, this is a two-part series. Last week we did all of this, and this week we're going to be doing all of this. So first, we have to define what a group is. If you ask a chemist what is a group, they'll just say groups are symmetries of space. Like this molecule has a symmetry that we can classify, and that symmetry, it's got all these reflections and rotations that we can kind of that it's symmetric around, and that forms a group of that. So the chemists will call that it has tetrahedral symmetry. While this molecule has a different set of rotations that'll keep it invariant. And so this has a different symmetry than this one, because this one has like 90-degree symmetries. Well, this one doesn't, and this one has like 120-degree symmetries. But I guess this one does too. But they're different, we can classify things by their symmetries. And while this is a kind of nice picture to have when you're thinking about groups, really, in a kind of Magretian sense, these are not groups. So does anyone know what this painting's called?
Seems French.
It is French, yes. This is René Magritte's The Treachery of Images. And so kind of putting on my art criticism hat for a second, one interpretation of this is that this is an image. Fundamentally, this is not the text. This is not a pipe. Fundamentally, this is an image of a pipe, and you can't actually smoke it because it's just an image. And so in a similar vein, those sets of symmetries that the chemists will call groups are not actually groups. They are just representations of groups. And so what the mathematician will call a group is something a little more abstract. So for the mathematician, a group is a set equivalent to an operation. Last week we called this operation addition because we were working in abelian groups. But this week we're going to call it multiplication because I think mathematicians have this underlying feeling that multiplication is somehow less commutative than addition. Even though, in the real numbers, they're both commutative, but one feels more commutative than the other. And also I want you in the back of your head thinking about matrix multiplication, which is not necessarily commutative. This operation has the existence of one kind of multiplicative identity, where 1 times anything is anything. And inverses, this should be 1. Such that inverses work how you expect, and also this operation is associative. Again, thinking with kind of matrix multiplication in the back of your head. And so the power of this abstract definition is it lets us see kind of how symmetries are related to each other. Going back to that tetrahedron example, the symmetries of a tetrahedron are isomorphic, where isomorphic means they're kind of structure preserving. They've got the same structure between the groups. This is isomorphic to the set of parity preserving permutations on 4 points. And this kind of makes sense. You think if you allow reflections like tetrahedrons, they can take any of the 4 vertices to any of the other 4 vertices. But some of them are going to be reflections. So it's only the parity preserving ones that will be in this rotational symmetry group. So correspondingly, this octahedron is the symmetries of this octahedron are isomorphic to general permutations on 4 points. And this is a little harder to see, but you can kind of think of it with these opposite kind of faces. And by rotations, they get permuted to any other pair of opposite faces. And so there's 4 of those, so 4 general permutations. But the real power of this kind of abstract way of thinking about groups is that you see this icosahedron has its symmetries are isomorphic to A5, which is the parity preserving permutations of 5 points. And while here we had nice kind of visual depictions of that, it's not at all obvious what the 5 points here that are being permuted are. And I tried looking, because sometimes we'll have these nice geometric kind of visualizations of things from group theory. It's really seemed like this is something that's fundamentally, because they have the same structure, so it's fundamental, and yet it's kind of abstracted away from the symmetries. And so in this way, this mathematical notion of group is much more flexible in what it can describe than the kind of chemistry symmetry of the space can describe.
So,
Yes.
so you mentioned that these more abstract definitions, you're saying these are isomorphic to the sort of this these three-dimensional objects that chemists refer to as groups, right?
I don't want to do the set of three-dimensional symmetries. It's not so much about the objects themselves, but under what rotations they're in.
Okay. Okay.
Yeah. You can imagine in fact, here's a little exercise, is where is the cube, like when we have three of the platonic solids, where's the cube and where's the dodecahedron here? And so if you actually work it out, you'll find that the cube has the same set of rotational symmetries as the octahedron, and the dodecahedron has the same set of symmetries as the icosahedron.
Okay.
So they're different objects, but they have the same symmetries.
Yeah.
And so now, once we have the definition of a group, we can start talking about group representations. Which in the back of your head, you should be thinking about this, where it's an action of the group on a vector space. So you would basically assign, what this ends up meaning in practice is this is a little more technical. It's a map from your group to the set of invertible matrices such that it's multiplication preserved. So we've seen with these kind of other symmetries, it kind of makes sense that these will be actions on vector spaces. But we can even go beyond these kind of like discrete symmetries and try and work out some other examples just with this definition alone, kind of other examples of representations that we may have seen in quantum mechanics. And so one of these is SU2. The representation theory of SU2 is well studied. And so as an example, we can represent any rotation as a matrix in SU2 just by this kind of general formula for how operators work that you will have seen in quantum mechanics. We have that three-dimensional rotations in quantum mechanics are given by matrices in SU2. And so since we have this map, we see that this group of rotations is just a representation of SU2. But it's important to note that this representation is a little different than the ones we've seen with these point groups of polygons, the polyhedra. And this representation is not a faithful representation, where a faithful representation is injective. But here with this SU2 representation, we have two matrices that map to the same kind of underlying rotation of SU3, as SO3. And so in general, if we try to like invert the map, you're not going to be able to. It's not invertible, right? But what if we tried it anyway? And so that ends up giving us a projective representation, which is a representation up to some rescaling phase factor, or alternatively a map from this space to a slightly different space of the projective general linear group. And so we see that SU2 is a projective representation of SO3. And in general, these projective representations don't lift your ordinary representation. As an example, you can see kind of this one, where you imagine kind of, this is a real representation where you have SU2 mapping 90-degree rotations. And you might be wondering, how does that make sense? Like if you have a point here, do a 90-degree rotation, do another 90-degree rotation. You're not back to where you started, so how can that be a representation? But if you instead think about lines through the origin, you have like a horizontal line, and then you have a vertical line, and then you're back to the horizontal line again. So it is, if you work in this projective space where you're not thinking about the matrices themselves, you're just thinking about matrices up to rescaling, which is the same as these lines, because you can just rescale things with one line. Then you do have this projective representation. Okay, any questions about this stuff?
Yeah, I guess I was wondering if you may just do a very, very quick review of like SU2 as a group. How is it defined?
So SU2 is the special unitary group. It is the group of unitary matrices, 2 by 2 unitary matrices with determinant 1. And this kind of shows up all over in quantum mechanics, where you're thinking about, like your rotations are given by, like fundamentally if you take quantum mechanics, you've seen the rotation operator, that is fundamentally living in the special unitary group.
Okay, cool.
You can also think about unitaries act on qubits,
Yep.
and so this is, and we usually don't care about the phase factor, so we generally like to describe like single qubit unitaries as living in SU2.
Okay.
So kind of one of the very powerful things in math is that although these projective representations don't generally lift to an ordinary representation, they do lift to an ordinary representation of a central extension of the group. And this is one of those kind of mind-blowing facts that pops up all the time in physics, where we have because we care about projective representations a lot in general, but they're kind of hard to work with, so I much prefer to work with ordinary representations, which we can always do by looking at a central extension of the group. A central extension is just, you intuitively should just think of it as you start with the group G, and you add elements into the center to make a bigger group. But more formally, it's this. It's this bigger group that has this abelian group as a quotient, and such that the abelian group is in, it competes with everything in G. And so when I say this comes up all the time in physics, I mean literally I was talking to Alice yesterday, and she mentioned that literally right now in QFT they're talking about projective representations of the Poincare group on spacetime. Because you want representations up to global phase, because everything is only up to global phase. And so that matters a lot in quantum field theory. And of course, my favorite example of this is that when all of you take string theory, you're going to learn about something called the Virasoro algebra. And you might be wondering, why would we care about the Virasoro algebra? Well, since what we really care about is central extension. What we really care about is projective representations of the Witt algebra, which come from ordinary representations of the unique central extension of the Witt algebra, which is the Virasoro algebra. And so I'm gonna give you a little program for how we're gonna make magic happen. So we can start by picking one of these point groups, these like chemists favored, whatever, symmetries of molecules in SO3. So then if we pick this subgroup, then we automatically get a projected representation of that point group in SU2. But then that lifts to a central extension of the point group that's naturally a subgroup of SU2. And in this way, we kind of pick out special subgroups of SU2. Do you like the sound of this?
Can you define what's a point group?
Oh, point group is just it's a chemistry term. It's the like symmetries that fix a point in space. So we're thinking about rotations and also sometimes reflections.
Okay.
Just in 3D space.
Okay.
Like here I'm saying no reflections because it's SO3.
Yeah.
And so let's see what kind of new groups we can cook up out of this. And so the paper, going back to the paper, it mainly, for the first part, it touches on these three, which are kind of interesting central extensions of these point groups. We saw the octahedral group, the tetrahedral group, and this is the Klein-Ford group, which you can think of as kind of pairs of reflections. So the Z2 is like a single reflection, and this is pairs of reflections in 3D space. So these are groups with second orders. If you do the central extension, you get these orders. And then you can also write these explicitly in terms of generators. And the whole reason I did this whole thing at the beginning was because I saw this and I didn't know what to make of it. Yeah. This seems much less clear than this whole discussion of central extensions. But they're fundamentally the same. That's just what the groups are. And so the natural question is that I had, and I don't know the actual answer to this, but I'm going to make up an answer. Was that we saw there was this icosahedral group that kind of completed the set of Platonic solid symmetries. And so why doesn't the paper talk about that group? Well, it's because fundamentally, when we're working with the fast Fourier transform, which is what the paper is ultimately aiming to build up to, we care a lot about the subgroup structure of our group. And so, as it turns out, the subgroup structure of this group is the icosahedral group, or A5. is radically different from any of the other point groups. In that, then this has like profound implications in math. So we call this A5 is not solvable, and all the other groups are solvable. And kind of the origin of this term and why it's so important in pure math is because you've heard of the quadratic formula, right?
Yes.
And perhaps you've heard of the cubic and quartic formulas, which are the analogs for 3 and 4 degree polynomials. But you haven't heard of the quintic formula, and that's because it doesn't exist. And the reason it doesn't exist is precisely because A5 is so different from A4, A3, A2, A1. All these other point groups, and so that's the origin of the name, is that these are all solvable, but the subgroup structure of A5 is so different that it's in its own category. And so that's one hypothesis, another just said it's too big, or they didn't want to work with it, or it's not, whatever. But that's the one I came up with. So now once we have these groups that we're going to try and find the Fourier transform of, let's actually define what the Fourier transform is so we can do it. And so when we're working with the Nonabelian case, it's a little more familiar because you got functions on the space to functional in the space. But this is what you get after you take the Fourier transform of a function in the non-Nonabelian group is something a little weirder. It's a map that takes in a representation of your group and spits out some matrix in some matrix space. And so you can just read this off from the definition. It's going to look something like that. And so kind of two natural questions arise then from this, which is how do you compute this and kind of what motivates this definition of the Fourier transform.
And so the f and f hats, they're the functions.
Yeah, so f is the function you want to take the Fourier transform of.
Yep.
And f hat is the Fourier transform of f, which takes in a representation.
Cool.
So how do you compute it? Because in theory, there's infinitely many representations, right? So how do you capture that all in a single formula? Well, just as numbers can be factored into primes, you can break any representation of the group into a sum of irreducible representations, which to save 8 syllables every time, I'm just going to call it irreps. And so we can kind of build every representation out of a finite sum of a finite number of building blocks, which are these irreps. Implicitly, I'm assuming the group is finite, and we're in C because that's the nicest place to do representation theory. But there's going to be this finite number of irreps that we can just compute, and then we can get the Fourier transform for any representation. The more interesting question is why this definition in particular? And to do this, we're going to take a look at the abelian case over C. And here we start introducing some of the magical facts of representation theory. The field's full of magical facts. You should definitely, everyone here should take representation theory if they get the chance. This is full of these magical facts. So magical fact number 1 is that every irrep of an abelian group is one-dimensional. And this has to do with the fact that the number of irreps is given precisely by the number of conjugacy classes of your group, which is not at all obvious, but it is true. And so magical fact number 2 is that the image of any group element under representation has to have norm 1. And this is a little less magical. It's just because if it didn't have norm 1, like you just keep taking powers and like it would not loop back around the identity, it would just keep going.
Yeah, okay.
Spiraling around. And so, as a consequence, all of the representations are elements of this set of maps from G into S1. Because you're thinking about the complex numbers with norm 1 under multiplication. Okay. And this is precisely the Pontryagin dual group we talked about last week. And so you see the abelian case is really just a special case of this more general non-abelian case. Any questions so far? Great. So if we want to actually implement this on a quantum computer, we need to ensure 2 different things. One, that it's actually a linear isomorphism between vector spaces. And the other is that it's unitary. These are both just basic things we have to check that are not obvious in the definition. So the Fourier transform is linear. And this actually is kind of obvious from the definition, so you just pull it out. But we have to introduce another magical fact here, which is that the sums of the squares of the dimensions of the irreps is the same as the order of the group. So as an example, we have this Q8 quaternion group Fourier transform. And so it acts, because it's a group of order 8, we start with 8 vectors. And so we have to end with 8 vectors, right? If we're going to have any hope of running this on a quantum computer. And so as it turns out, Q8 has 5 representations, 5 irreducible representations. It has 4 that are one-dimensional and 1 that's two-dimensional. And so as it turns out, the sum of the squares of the dimensions is exactly what we started with. Unitary is a little trickier, but we have another magical fact here, is that every representation is isomorphic to a unitary representation, and unitary representations are great. So we have that the image of any basis vector, we should think of basis vectors as kind of indicator functions that are 1 on the element and 0 everywhere else. And so if you plug that into your formula, you just get that as the direct sum of the image of G under all of the irreps. And so as it turns out, with the correct normalization, this is just the formula. But, last time we had this whole elaborate story about why unitarity should be the way it is in the abelian case. Here, just compute it out and it works. In general, it's related to some deep stuff with regular representation, but you can also just, because we're working with finite groups here, you can always just compute it out.
So this G here, what is this? This is like the state that's representing the
So in principle, you have this computational basis. In principle, all of these in the back of your head, these should all correspond to a group element.
Okay.
And so with a quaternion group, maybe this is 1, and this is -1, and this is I, negative I, J, negative J,
Okay,
negative
cool.
J. And so this is what the circuits end up looking like now once you've implemented it on a quantum computer. And you'll see here, it's what I said last time, right? Where the fast Fourier transform relies on the subgroup structure, and you see very explicitly the subgroup structure here in the circuit itself. So that it's just a bunch of, you start with the fast Fourier transform of the subgroup, and do a Fourier transform on the extra bit, and then find a way of weaving it all together. This is all elaborated on in the paper, so I'm not. And the technical weeds, this is like a high-level overview. I'm not going to get too into the technical weeds of the paper. And so here's the explicit example for that binary tetrahedral group, which has Q8 as a subgroup. And here right at the beginning, we see the fast Fourier transform of Q8. So that was all the first part of the paper. The second part of the paper does basically the same thing, but instead of special subgroups of SU2, you get special subgroups of SU3, which is unitary 3x3 matrices of determinant 1. And so in the first part of the paper, we had this bottom chain of subgroups. Now we have this top chain of subgroups. And apparently the paper says the reason to care about these groups is that they're useful in particle physics. I don't know anything about particle physics, so I'll just take them at their word. And here's it in terms of generators. There's no nice picture with predictive representations here, because SU2 can naturally this double cover of SO3, and we all like SO3, and SU3 is not that. So the generators are all you're going to get, and apparently they're useful in particle physics. So here's an example of the algorithm for delta 27, which is one of these subgroups of SU3. We see here a kind of similar thing with you have the Fourier transform at the beginning, and then a Fourier transform in the middle, and then some interweaving stuff in between. But this paper has kind of one last twist for us, in that it starts looking at Q-trit circuits. Now Q-trits are like qubits, but 50% better, because instead of 2 states, they have 3 states. I swear there was a company working on Q-trit architectures like 2 years ago, and I went to them at one of the the career tours. I don't know, I forgot who the company was. Possibly Inflection or Quantinuum. One of the two. But anyway, so Q-trits, like, you think with their classical computer, like, there's a good reason why zeros and ones, why it's just binary, because they're like high and low voltage, and it's kind of hard to read the middle. People have tried like 3-bit, like, well, I guess trits, that's where the name comes from, right?
Yeah.
They've tried trit computers, and there's a reason every computer is bit, right? But with quantum, like, if it's just like two different, like, say you're doing neutral atom, it's just like a ground and excited state,
Yeah.
right? Like, if you're doing spin qubits, like, obviously you have to have qubits. But if you're doing like neutral atom, which is ground and excited state, like, in theory, there's nothing stopping you from just going higher and having like a three-state system that you're using for computations.
Or multiple.
Or higher, general QDIT architecture. And maybe this is just my topological bias showing, because topological people don't care about like individual qubits; they just care about the Hilbert space. Because there's no clear way to really map it onto qubits.
Yeah.
But yeah, in principle, all of these could work. But in practice, it gets harder to implement. It gets harder both to keep the QDIT stable as D increases, and have all your single QDIT unitaries also get harder. But here you see an example where it actually gets much easier with qubits, because naturally there's a certain like 3-ness to all these S23 subgroups, and so you take this big algorithm and you just it simplifies down to this if you're working with qubits. And then there's also the option to do mixed architectures, where this is for delta 54. Which is a group of order 54. So you can make it out of 3 qubits and a qubit. And so that's what we have here. We have 3 qubits and a qubit. And it makes things this slightly easier. And we also see that this is delta 27 showing up because it's a subgroup of delta 54. Yeah, and so the rest of the paper is just like this. It's all just similar constructions, a little more specific about what exactly these representations are. I didn't quite tell you because it would just be me reading off numbers. Okay. But in general, that's the wisdom this paper has to share, and that's in general what it's trying to say, is that you can implement these non-abelian Fourier transforms efficiently on a quantum computer. So, are there any questions?
Well, everyone, let's first give Ryan a round of applause.
Thank you.
Presentation. Yeah, Jamie, if you have any questions. Well, I had a question about, I guess, the definition of the non-abelian Fourier transform, which you gave as, I think it was like the sum of like functions.
Yes.
So first, like, why is this outputting a matrix? Is f of g?
Because rho is a matrix. Rho of g is a matrix.
Okay, we're assuming that the representations we're dealing with for g is like it's in matrix form.
Yeah.
Okay.
But we're working. Everything's fine here.
Okay.
Infinite dimensional representation theory is its own beast. That's very useful and interesting. But because we're working with irreps of finite groups in general, like past this slide.
Yeah.
And those are all finite dimensional.
And then f is maybe like the wave function, for example, that's represented.
Yeah. So f, the way you describe a function on a group on a quantum computer is just you can treat we saw you could treat the elements of the computational basis as elements of the group.
Yeah.
And so functions are then specific superpositions of elements of the computational basis. It's the same with the abelian case, where we encoded functions as superposition of computational basis.
Okay. And you're saying that in order to realize this Fourier transform, you first have to show that the sum is, like the number of row is finite, which you show with the irreducible representations. Then you have to make sure that it's unitary, like
So, right, you need to ensure these are magical facts from that theory. Another magical fact here that helps you is that the number of irreps is equal to the number of conjugacy classes of your group. So it's always, in principle, like it's always going to be finite.
Which okay, and it shows the linear isomoorphism. By
and the linearity just comes from, you know, like AF plus B. You can always take it out of the sum.
Yeah. Okay. And I'm just curious, like, what kind of I guess, why is the non-Nonabelian Fourier transform, like, I guess, useful in terms of, like, because we talked about how, like, last week we talked about how Shor's algorithm is, you know, implemented with the abelian Fourier transform. So is there like I guess an example of the application that you could use?
Great question. I really don't think so.
Okay.
But like, this isn't to say the non-Nonabelian transform is not useful. They mentioned applications of particle physics that I just glossed over.
Okay.
And in general, in pure math, it's useful whenever you have functions on groups.
Yeah.
Which, you know, happens. It happens.
Yeah.
To be able to do this non-Nonabelian Fourier transform.
Cool.
But like, you're gonna have nothing that's like Shor's algorithm.
Yeah. And I think this
because
is
Shor's algorithm is such a high bar for quantum
yeah.
computations.
And I think that it's like a cool generalization.
Yeah,
of
exactly.
Abelian Fourier transform as well, which is something that's always good in math, is to get better generalizations.
Yeah. Cool. And there's been some pretty recent results, just kind of in the sphere of representation theory, where we've seen some proposed quantum algorithms for computing these certain coefficients with regards to representations of the symmetric group. So it's being used as like a computational tool for math as well.
Okay.
Or will be when it gets actually put on a useful quantum computer, which is only 5 years away. So.
You never know. Maybe it's tomorrow.
Yeah, well, maybe it's 2027, as both PsiQuantum and INQ exist. I actually don't. I don't think they exist anymore, which is a good thing. But they definitely said it at one point.
Okay. Let's see. If there's, I guess there's no questions on Zoom.
Okay. Well, thank you all for coming.
Yeah, thank everyone. Let's thank Ryan again for its very cool presentation.